Today we did a titration, and let's go over the things you need to know in order to do the calculations in your post-lab report. And the goal is to get a KF, to calculate a KF. In order to calculate a KF, we need to know n, we need to know x squared, we need to know this alpha fraction thingy. Now we are going to go over how we can find all these three items. First of all, this is the equation. Metal reacts with EDTA, get this metal EDTA complex. The first assumption we make here is that at the end of the titration, all reagents were gone. All we had was this complex, this metal complex MEDTA, and this complex breaks down to reversible reaction, breaks down to form this metal ion and this EDTA. So 1 to 1 to 1 ratio. So how do we get the mole of this complex? To get the mole of this complex, we use the mass. You weighed the manual says around 0.1 gram. You use maybe a little more, a little less than 0.1 gram. You use your real data. Here, around 0.1 gram of the metal salt divided by the molar mass of the metal salt. The molar mass of the whole metal salt, not just the metal ion. When you look for the molar mass, it should be the molar mass of the whole salt, metal salt, not just the ion. So mass divided by that molar mass, you get a mole, and it's the same mole as this complex. This mole divided by 56. Why 56? Because here we assume you use the 6 mu of EDTA. And in your case, you use your real number, whatever EDTA, how many mu you used. You use your own data. But here we assume 6. So mole divided by 56, the volume will get a molarity. This molarity will decrease as this metal complex breaks down into reagents like metal, ion, and EDTA. So decreased by x, and these two reagents increased by x. So when it's equilibrium, the molarity of this metal complex is this thingy, number of mole divided by 56 minus x. And these two at equilibrium would be x. We make another assumption here. I think in general chemistry you should have used this assumption before. Yeah, there. So when the dissociation rate is so small, we ignore this part, the x. So if we assume this x is so small, we ignore it. So in the end, this n, we use n to represent the molarity of the metal complex at equilibrium. This is n. We use n to represent this part. It's the same as this one because we assume this x is too small and we just ignore it. So here, we know how to calculate n. We also need to know how to calculate x squared, and we also need to know how to get this alpha fraction thingy. So here, KF prime. This KF prime is not pH dependent, and we can find this KF prime in a table, so it's known. We don't calculate. We still need to do a little bit of a conversion, but it's easy. We consider this a known value. So we can find this in a table, and we know how to calculate n here, and this is known, and we have this equation. We can find the x squared. In this way, later on I will show you how to find this KF prime in a table, and this equation, we will use this equation to find this x squared. Now we have n, we have x squared. We need to know how we can get this alpha fraction thingy. Now it's also in a table. It's in a table too. Now let's go to the tables, and I will show you how to get this KF prime and alpha thingy. First of all, the kf prime, in that equation we use the kf prime, but here in this table it's kf. It's the same thing. It's a little difference, a little confusing, but it's the same thing. This kf is that kf prime. The ions, you can pause this video, by the way. You find the log kf, and then you do a little bit of conversion, you get the kf. And the kf, after the conversion, you get this kf. This kf is the kf prime we just talked about. And now the alpha thingy, the fraction thingy, now it's here in this table. The pH values I give you already in this announcement. In the announcement, I give you the pH, or you some of you maybe you did that pH measurement yourself. That's fine. That's okay. And I also give you the number in this announcement, and we round it up. So if it's 2.8, we round it up to 3. If it's bigger, the decimal place is bigger than 0.5, you add 1 to whatever number it is. For example, if it's 3.7, it's 4. But if the decimal place that the number is smaller than 0.5, we ignore it. For example, 4.3 would be 4. We just use it as 4 that way. So based on that, you can find the alpha thingy here. And you have alpha thingy, you have x squared, and you have n. You should be able to calculate this kf. After you calculate this kf, you can use this for other calculations in your post-lab report. Alright? So good luck.